Hello, class 12th physics, chapter moving charge and magnetism, important questions. What is the direction of force acting on charged particle Q moving with velocity v in a uniform magnetic field B? So, magnetic force it will experience, and that will be given by F vector equal to Q v vector cross B vector. Alright, it is not asked here, but the direction of force is given by right hand thumb rule, because V, if this is V and this is B, this is V, then V cross B. The order of V cross B is taken in this form. Alright, so this is called right hand thumb rule. These two vectors are in a plane, then curl of finger along these two vectors, V cross B, then direction of thumb will show the force acting on it. So this is, I have drawn a 3D diagram, so this will be the direction of force. These are lying in a plane, and so it is perpendicular to that. If it would be B cross V, then we have to take it in this direction, B cross V, from first vector towards second vector, V cross B, from first vector towards second vector, so this way. Next, why should spring of moving coil galvanometer have low torsional constant for greater current sensitivity and voltage sensitivity? Actually, current sensitivity IS is equal to NAB upon K, where K is torsional constant. So lower the value of torsional constant, greater is the current sensitivity. And in the same way, voltage sensitivity is NAB upon KR, KR resistance. So in both the cases, torsional constant must be as small as possible. Next, magnetic field line can be entirely confined within the core of toroid, but not within a straight solenoid. Why? So the answer is, in solenoid, at the ends, magnetic field lines diverge, but in toroid there is no end. So all the magnetic field lines confined within the toroid. Next, electron does not suffer any deflection while passing through, an electron, कोई भी electron does not suffer any deflection while passing through a region of uniform magnetic field. What is the direction of magnetic field line? So remember one thing, magnetic force experienced by a charged particle is given by F equal to QVB sine theta. Now there are two possibilities. One, if theta is equal to 0, and second, if theta equal to 180 degree, F is equal to 0. So here we can conclude that in such a case, we can conclude that direction of magnetic field line is either along or opposite to the direction of velocity of electron. If it is not experiencing any force, either it is moving along the direction of magnetic field or opposite to the direction of magnetic field. A beam of alpha particle projected along x-axis, we know alpha particles are positively charged, experiences a force due to magnetic field along y-axis. What is the direction of magnetic field? We have to draw this. Okay, so I am drawing coordinates. Alpha particles are projected along x-axis. These are the direction of alpha particles. Experiences a force along y-axis. Okay, now we are not certain that it will be z-axis. It can be positive z-axis, it can be negative z-axis. So of course z-axis will be the answer. So here we will apply that Fleming's left hand rule. So this is the direction of force, upward. This is the direction of positive charge. This is the direction of positive charge. So I mean motion of positive charge. So now my first finger, index finger, is pointing in toward paper. That will be the direction of magnetic field along negative z-axis. Now same question with electron. So let's see what will happen. Now electron is moving along x-axis and it is also experiencing force along y-axis. Now remember one thing. For electron or any negative charged particle, we have to take opposite direction for its for equivalent positive charge, because this rule is applicable for positive charge. So now charge is going that way. Actually it is something like this. Now force is in upward direction, I mean y direction, and middle finger is along negative x-axis. So first finger is pointing out from the page of plane of the paper, that is positive z-axis. So answer is along positive z-axis. So whenever there is electron or any negative charge particle is given, what you need to do is you have to just revert its direction, just to take opposite direction for equivalent positive charge. Depict the trajectory of a charged particle moving with velocity v as it enters a uniform magnetic field perpendicular to direction of motion. So it's very simple. We'll draw this inward magnetic field, much convenient, and it is entering, positive charge is entering. This is plus q coming with velocity v. So what will happen, actually it repeatedly experience a force in perpendicular direction. First it will go up, then it will, now it is going upward, so force will be experienced this way, then it will go that side. So ultimately it will follow a circular path. This time here, this time here, this time here, and this time here. So ultimately it is following a circular path. See, if it is going upward, force is experienced this way, leftward, and then if it is going this side, then force is downward, because each time index finger is downward because of magnetic field. So you can see, and here it is going now down to the page, and charged particle is going from up to down, and so force will be experienced from left to right, and finally this. So ultimately it will follow a circular path. Next, write the expression in vector form for magnetic field, magnetic force F acting on a charged particle moving with velocity v in the presence of magnetic field B. So that is the same, and the same can be asked in terms of Lorentz force also. Actually Lorentz force is a bit complicated. It includes electric field also, but they can say that in the absence of electric field, state the expression for Lorentz force. So simply it is F equal to Q V cross B. That's all. They haven't given any angle or something else, otherwise we would write it in scalar form, that is F equal to Q V B sin theta. Not required here. Alright, using the concept of force between two parallel current, define 1 ampere. So actually this F12 is equal to mu naught upon 2 pi I1 I2 upon R into some L. So this is the expression for force between two parallel currents. And what we conclude from here, that F upon L, force per unit length for both the currents, is same. So in order to define 1 ampere current, what we have to do, I1 equal to 1, I2 equal to 1, R equal to 1 meter, this is 1 ampere, this is 1 ampere, this is what we have to define, and L is also 1 meter. Then numerically F will be equal to this value, and numeric value of this is actually alone, this alone has some other units, but entire these unit will also be adjusted there. So it will be 2 into 10 to the power minus 7 Newton. Someone can say that if now F is equal to this, then how can we write its unit as Newton? Actually, from meter will go from here, ampere will go from here, meter will go from here, and then there will be some readjustment in the unit of this quantity, and finally we will get Newton. So force is 2 into 10 to the power minus 7 Newton. Now how are we going to define it? So 1 ampere is that current which, when flows to infinitely long parallel wires placed in vacuum 1 meter apart, attract or repel. Actually, if you know about the theory of it, so you might know that if currents are in same direction, then they will attract each other, and if they are in opposite direction, they will repel each other. But we are interested in force only. So attract or repel unit length, that is 1 meter, by a force 2 into 10 to the power minus 7 Newton. So this is a complicated definition, but what you need to remember that first thing, this formula is derived from the formula of straight conductor, magnetic field due to straight conductor, and that must be infinitely long. That is why this infinitely long term came here. They placed in vacuum, mu naught is there, so placed in vacuum, 1 meter apart because we have taken that, attract or repel because they can, unit length of 1 meter by a force this. So you need to just include all the terms, keep this formula in mind, and these are the terms. See, your definition, your word arrangement can be different, but what you need to put into it is this thing: infinitely long, placed in vacuum, 1 meter apart, repel 1 meter length, and this force. These are the key points. If you could able to arrange it of your own in a meaningful sentence, then that will be accepted definition. Otherwise, just memorize this. Write the condition under which an electron will move undeflected in presence of crossed electric and magnetic field. So there is very interesting thing. So when V is equal to E by B. Direct answer. But how it has arrived? So let us suppose we have an electric field directed this way, and we have a magnetic field. And now if a charged particle is entering into it, then okay, if it is an electron, so it will have tendency to move this way. And now this is an electron, so consider it as a positive charge, so it's it will be going this way, a positive charge. It is equivalent to a positive charge which is going this way from toward left. And magnetic field I have put cross, so magnetic field is inward. So it will experience a force in downward direction. So you can see, due to magnetic field, it will be pulled downward. So there can be a condition. So in detail, we can do it like this. We have to draw this, and then we can say that in equilibrium, QE, I'm going too fast. Force due to electric field is equal to force due to magnetic field. And it is QE. We know in electric field charge experience QE force, and it is QVB. QQ will get cancelled, so V equal to E by B. So it is not only for an electron, it is for any charged particle, and this arrangement is called velocity selector. A charged particle of mass m, charge q, moving with velocity v, enters in a region of uniform magnetic field at right angles in the direction of its motion. Find change in kinetic energy. Change in kinetic energy is 0. The reason, since force experienced by Q is perpendicular to velocity. So only direction changes, not the magnitude. So initial speed is equal to final speed. So initial kinetic energy is equal to final kinetic energy. And that is why change in kinetic energy is zero. Write the principle of moving coil galvanometer. When a current carrying coil is placed in a magnetic field, it experiences a torque given by tau equal to NIAB sine theta. And we need to explain what are these terms. I'm just asserting them, where N is number of turns in the coil, I current flowing through the coil, A area of cross section of the coil, B magnetic field in which coil is placed, theta is the angle between area vector and magnetic field. Next, a coil of area A carrying a steady current I has magnetic moment M. Write the relation between M, I, A in vector form. So remember, M is equal to I, A. A is vector, so this is the okay. And what about its direction? Actually, its direction is along the normal to the surface, and especially it is given by according to right hand thumb rule. Okay, so next, define magnetic dipole moment. So actually we have this formula, but we have another formula, which is, because we know that the magnetic dipole experience torque which is given by mb sine theta, and maximum torque is given by mb. From here we can define magnetic dipole moment. So magnetic dipole moment of a magnetic dipole, I just assert these things, don't just copy whatever I am writing. It is magnetic dipole moment, you have to write it in full. Magnetic dipole moment of a magnetic dipole is equal to torque experienced by it, maximum torque experienced by it per unit external magnetic field. Alright, here indicate the direction of magnetic field due to small element dl. So very silly question actually. If we grip this current element like this, then magnetic field line come out and go inside. From here it will go inside, that way it will go like this. So at P it is along negative x-axis, along. That's all. Same question can also be asked in terms of Biot-Savart's law and all that. So what we have to write in that case, let us suppose this is, they have given x. So in that case dB will be equal to mu naught upon 2 pi I dl vector cross this time x upon x cube, because if they have given, but here it is not asked, they have asked just for the direction, so we did this. We can find direction by this also, because dl is along z direction, x is along y direction. So dl cross x, this time for vector product we do this way, dl cross x. So it is going inward means that way, that is negative x-axis. Or simply see, two times I am doing this. Either we can grip the current, then curl of the finger is showing magnetic field passing from this point. And this is here also I am using this right hand thumb rule, but for this time I am using for cross product. For cross product, as I told you, the order, see the order, from dl to x we have to curl our fingers, dl to x. So it is going inward. Thumb is pointing inward. This is coming outward, positive x, so inward, negative x. That is the direction. How is magnetic field inside a given solenoid made strong? Oh, class 8th question. By increasing current. Number 2, by placing soft iron core. Or any other ferromagnetic core. Okay, write the expression for Lorentz magnetic force on a particle if charge of charge q moving with velocity v in a magnetic field B. Show that no work is done by this force on the charged particle. So we did this earlier also. So I am not putting more effort here. So this is q moving with velocity v, so ultimately it will follow a circular path. Repeatedly, by repeated force, it will ultimately follow a circular path. See, this is the direction of force each time. And since force is perpendicular to velocity, so only direction changes, not the magnitude of velocity, I mean speed. So u is equal to v, and therefore kinetic energy initial is equal to kinetic energy final, and we know that work done is equal to delta Ke, which is equal to 0. Now, two identical circular wires PQ, each of radius r, I haven't mentioned here, and carrying current I, kept perpendicular plane with common center as shown in figure. Find magnitude and direction of magnetic field at the center. Very interesting one, very interesting one. So what we need to understand here, if it would be a single loop carrying current this way. So first grip this current. See what I am doing. If this is current, this is magnetic field. But if, wait a minute, this is current flowing here. So grip that current. Means if current is curling, then you can put your finger along the curl and then thumb will show the direction of magnetic field. And if current is straight, then put your thumb along the direction of current. So if current is curling, then put your fingers along the curl. At that time, I'm drawing it here. If this is the current, so this will be the direction of magnetic field. And if this is the current is in this way, then thumb will show the direction of magnetic field. Vice versa. So yeah, you can see here, current is going this way, so magnetic field for Q, this will be the direction. And for this, direction will be upward for P. You can do this in the exam. Make them separately. So what we have to do now, we can write BQ is equal to BP. By magnitude both are same. By magnitude both are same. For loop magnetic field is mu naught I upon 2R. That's all. And I'm putting it equal to X. Actually that will be helpful for us. So now what will we do? We can do one thing. We can superimpose both of them. So it will look like this. That this is BP and this is BQ. And I have considered both value as X. So this will be their resultant. That will be B. So B will be root of BP square plus BQ square. That is root of X square plus X square. That is 2X square. And that is X root 2. And that is X is mu naught I upon 2R root 2. This will be the direction. And remember, if two vectors are equal, since two vectors are equal, so resultant will be the bisector, angle bisector of angle between them. That is at 45 degree from the direction of magnetic BP or BQ. Or we can say resultant is along the angle bisector of. So next question, two identical loop PQ, each of radius R, whereas current 2I and 2I. Okay, so this is the situation. So you can imagine that you are sitting in your room, and at the center of room, and two opposite walls, there are, in one of them there is a coil carrying current in clockwise direction, and in opposite again in clockwise direction. So remember, this is at the axis of the coil. So R is the distance. All right, so what will happen here, B at O will be equal to, actually this wasn't given here, but I have marked this because for first coil magnetic field is like this, actually current is like this, so magnetic field going this way, and here current is this direction, so magnetic field will go that way. So ultimately magnetic field due to this coil is in this direction and this coil is in this direction, so we can write BQ minus BP. Why not to BP minus BQ? Yeah, we can write that. Answer will come in negative. That's totally acceptable. All right. So for axis, magnetic field is mu naught I R square upon 2. Oh, that is R square plus X square power 3 by 2. So for Q it is 2I, and mu naught I. For P it is I. R square upon 2. R square plus X square power 3 by 2. So now what? Actually X is also R, so that will be 2R square. So first what I am doing, this is twice of this quantity, this is singly that quantity. So if we subtract both of them, see, 2 entire this minus 1 entire this, so that will be 1 of entire that. So that will be mu naught I R square upon 2R square. Why I did this? Because X is also R. X is also R in this question. So that will be, okay, so I skipped 2 terms here. First thing what I did, I subtracted both of them and directly put here. And second thing, I put the value of X, added both of them, and that is this. So power 3 by 2. Now finally it will be mu naught I R square upon 2, and 2 to the power 3 by 2 means 2 root 2, and then R square multiplied by 3 by 2. That will be R cube now, and R cube will get cancelled with R square. So finally it will be mu naught I upon 4 root 2 R. In the same way you can try this out. So it's a similar question, but this time currents are equal, so try it of your own. All right, here coil of turn n, radius r, carrying current I. Write expression for magnetic field at the center, mu naught I upon 2r, and magnetic dipole moment. So this is the first and this is second. Magnetic dipole moment m equal to IA. Actually n is also there, NIA. So we can't leave it as it is because A is not given, instead R is given, so we will write Ni pi r square. Actually we can't use R symbols, what we have assumed. We have to use whatever given in the question. A solenoid, okay, same question for solenoid. Remember, solenoid and coil, there is difference. For solenoid, L is very, very greater than radius. So both are actually, in physical appearance, both are coils. But if its length is lesser, then it is called coil. But if length is longer, it will be called solenoid. So, but it is not of any use in this question. So here, magnetic field due to solenoid is mu naught small ni, which is mu naught ni upon n. This is the magnetic field due to solenoid. And what about magnetic dipole moment? So that will be NIA as it is, so it will be NI pi r square. Next, a proton and a deuteron, they will not give these shortcuts, they will write it in full. A proton and a deuteron. What is proton? Proton charge E and mass, let us suppose m. Deuteron charge E plus E. Don't consider it as electron, plus E and mass 2m. It has mass double that of proton. Actually, deuteron is deuterium, hydrogen having a proton and a neutron. So, moving with velocity v, enter in a region of magnetic field V acting perpendicular, trace trajectories by establishing relationship between them. So, first, what we will do when charge particle enter magnetic field perpendicularly, then its path it follows a curved path. If magnetic field is full enough, adequate, then it will perform a circular motion. So, all right, I'm directly pointing this toward a circular motion. Then it will follow a circular path. All right. So, centripetal force for circular motion is equal to magnetic force, and that is mv square by r is equal to qvb. And when we will solve it, then r will be equal to mv upon qb. Here q is same, but m of deuteron is equal to twice of m of proton. So, radius of deuteron orbit will be twice that of radius of proton axis. Now we can draw it. This is a 1 mark question, remember. If in 2 mark, then you can do all these working. In 1 mark, you can directly draw. So, if both particles enter proton plus deuteron, then now they will get separated, because deuteron will follow a bigger path and proton will follow a circle of half of the radius. So this is proton and this is deuteron. That's all. Find current flow. Find the current flowing in a wire which produces magnetic field. Okay, so that's a very simple question. We know for a straight wire, B is equal to mu naught I upon 2 pi r, and from here we can find it out. B is given 10 to the power minus 5. Mu naught upon 2 pi is given to, actually we know it is, actually mu naught is 4 pi into 10 to the power minus 7. So that's how we can find out this mu naught upon 4 pi, mu naught upon 2 pi. I, we have to find r 2 centimeter, we have to convert it, minus 2. So finally it will be I equal to, I'm directly doing it, I'm directly doing it, and I hope you people will understand this. 1 ampere. Okay, a square coil A is this, 200 turn carrying 5 ampere current. It is placed in a uniform magnetic field. Calculate torque. All right. Okay. Perpendicular to its plane. Earlier it was perpendicular to its plane. So we don't have to find torque at this condition. We have to find torque when angle is 60 degree with plane. Remember, whenever we take the direction of magnetic field and this coil, we find the direction between B and A, area vector, not the plane of the surface. This is not considered as theta. This is considered as theta. So here, first thing what we have to do, if in the question, remember this thing, in the question, it is written that angle from the normal to the plane is this much, then you have to directly put that value. But if angle is from plane of the coil, then if it is taken from the plane, then subtract it from 90. Remember, if it is given that angle, that magnetic field line is at an angle so and so from the normal to the surface, then use that angle. But if it is given from the plane of the surface, then subtract it from 90. So, and now we can put the value, tau is equal to mb sine theta. So m is nia, Ni AB sine theta. N is 200, I is 5, A is 10 to the power 2 centimeter square. It means 10 to the power 2 multiplied by 10 to the power minus 4. Now it is in meter square. B is 0.2 and sine 30. Sine 30 will be 1 by 2. So finally, okay, what I'm doing now, 2.2 and 5. If we multiply both of them, it will result 1. So I'm removing these two. So now there will be 200 into 10 to the power minus 2 into 1 by 2 by this. It will be 100 means 10 to the power 2, 10 to the power minus 2, finally 1 Newton meter or joule. Okay, next, a charge q of mass m moving with velocity v perpendicular to magnetic field B. Deduce expression for radius of circular path. I did it earlier, so I'm directly writing it here, mv upon qb. You can go back and watch that video in which proton neutron were given. So that is how we are going to derive this expression. A proton and an alpha particle with same kinetic energy pass through uniform magnetic field perpendicularly. Find ratio of circular orbit of their radius described by them. So we know that r is equal to mv upon qb. mv is momentum, momentum upon qb. And there is a relation between momentum and kinetic energy. And what is that relation? Root 2m kinetic energy upon qb. Now we can proceed, because they have asked for the ratio between actually whenever such type of question comes, ratio and all that, you have to set a formula for that, and afterward you can do as you wish. So now proton to alpha, actually rp by r alpha, that will be equal to root 2m of proton kinetic energy. They have same kinetic energy, so I'm not putting any subscript over this kinetic energy, upon charge of proton magnetic field. Magnetic field is also same, so I'm not putting any subscript for that. 2m of alpha kinetic energy upon q of alpha b. So when we simplify this, it will come out to be q alpha by q proton multiplied by root of mass of proton by mass of alpha particle. So charge of alpha particle, we know charge of alpha particle is 2e, charge of proton is e, root mass of proton. If we take it m, so mass of alpha particle will be 4m. We'll solve it, it will come out to be 1. How? I'm not going to tell you. So 1:1 is the ratio. Now using information given following figure, find force and torque. So here first we have to find forces on each branch. So I'm writing it A, B, C and D. So on AB, see, now we will apply that flaming left hand rule. Current is going this way. Magnetic field, first we have to grip this wire, this current. So magnetic field will be pointing inward. So we will have here inward magnetic field, here also inward magnetic field. So magnetic field is going in, current is going this way, so it will experience force in upward direction. So AB will experience force in upward direction, and BC will experience force like this. It's like this. Current is going this way, magnetic field inside, so force is acting downward. So BC will experience force in downward direction. Force on AB and BC cancels each other. Okay, now what about AD and BC? So AB, AD, I'm directly writing FAD is equal to. So force on FAD, both are in same direction, so it will move this way. So we will use this formula, mu naught I1 I2 L upon 2 pi r. So, and same force will be experienced by BC. It will experience, actually distance will be different, so not the same force. Alright, so we need to calculate this. Mu naught by 4 pi is 2 into 10 to the power minus 7. I1 is 5 ampere, I2 is 2 ampere, and L is 10 centimeter, that is 10 to the power minus 1. I have converted it into meter. and distance between them is 2 centimeter. That is 2 into 10 to the power minus, well, what I can do, 10 centimeter, 10 into 10 to the power minus 2, and then 2 into 10 to the power minus 2. That will be much easier. So anything else I left? No. So the final answer will be, this is getting cancelled, 2 cancelled, 5 to the 10 and 10, so that will be 10 to the power minus 5 Newton. And toward leftward, I'm only writing left. Okay, next, force on BC is once again same formula. So 2 into 10 to the power minus 7 into 5 into 2, everything is same, 10 into 10 to the power minus 2 upon, only the distance will change. So it will now become 6 into 10 to the power minus 2. So now it will be, earlier it was this, so now it will be 0.3 into 10 to the power minus 5 Newton. You can calculate it, you will find this value. Okay, actually 3 to 2 decimal place. It will be along, okay, so this will be repelled. Actually we know, I'm not using any rule here, I'm directly using that you know, that direct reasoning, direct result. Direct result is, if currents are in same direction they will attracted, and if opposite direction they will be repelled. So here it will be repelled, so it will move toward right. So we can subtract both of them, and purposely I am writing it like this. So F net will be equal to 1 into 10 to the power minus 5 Newton minus 0.3 into 10 to the power minus 5 Newton. So that will be 0.7 into 10 to the power minus 5 Newton. You can adjust 0 and you can write it in the form of that order of magnitude and all that. So I'm not doing it. I'm interested in another thing which is of greater interest, is both forces are collinear. Actually one is going this way, other is going that way, both are collinear. So tau equal to 0, there will be no torque. So there is another question, a circular coil having 100 turn, radius 20 centimeter, lies in xy plane. A circular coil having 100 turns, radius 20 centimeter, lies in xy plane. With its center at origin, find magnetic field at okay, this much. Alright, so in terms of coordinates, sometimes it looks like a bit difficult. They haven't asked for vector form, so we have no problem with that. So what we are going to do in this question is this will be the distance on axis. So this is the question in which we have to find magnetic field on the axis. So what we are going to do here, B on axis is equal to, we know that it is mu naught I r square upon 2 pi, oh sorry, 2 r square plus x square power 3 by 2. Mu naught is actually 4 pi into 10 to the power minus 7 upon 2. I is actually n, because turns are also, I'm writing here. So now I is 2 by pi, n 100, r square 20 into 20 into 10 to the power minus 2 into 10 to the power minus 2 upon 2 is there, r square, oh, that is going to be a bit trouble, 400 into 10 to the power minus 4, and then this square, 400 into 3 into 10 to the power minus 4 to the power 3 by 2. I don't know how I am going to solve entire of it. Generally, okay, for a trick, what you can do, which I didn't, this is r and this is some multiple of that. So you can take radius as r and r root 3. This is r and this is r root 3. So it will be easier to calculate, but now it is turning to be difficult and difficult. So 2 will get cancelled, pi will get cancelled, Anything else what we can do here? This is 10 to the power 1, 2, 3, 4, and 4 power will get cancelled here. So the leftover thing is 2 to the 4, 4 the 16, 16 multiplied 10 to the power minus 7 divided by, okay, so now see this, consider this as x, consider this as x, so x plus 3x is 4x, so that will be 4 multiplied by entire this term. I think you people are getting what I want to say. This entire, consider this as a single term x, consider this, so this will also be x, so x plus 3x is 4x, so we can write 4 into 400 into 10 to the power minus 4 to the power 3 by 2, that will be 4 4 is 16. We can take root of that because there is 3 by 2 means root and then cube of it. You can do opposite to this also, you can first do cube and then take root, but I feel that root and then cube will be much easier. So it will be 16 into 10 to the power minus 7 upon, so I'm taking root, so 4 4 is 16, it will be 1600, so now it is 40. Why? Because 400, root of 400 is 20, and root of 4 is 2, 20 into 2, 40, multiplied by 10 to the power minus 2 to the power 3. So now it will be 16 into 10 to the power minus 7 upon, now it is, okay, now see the trick, I am writing it, okay, 4 into 4 into 4. Why I did this? I am adjusting this 0 with this, so that will be equal to 10 to the power minus 3. That is 1 by 4 multiplied by 10 to the power minus 4. So that is 0.25 multiplied by 10 to the power minus 4. So that is 2.5 multiplied by 10 to the power minus 5 Tesla. So that was simply a mathematical trouble, otherwise there was no problem. So this will be the final question, and there are many such type of questions. So I have just collected few from those questions, and in other video I will upload similar type of various arrangements, various possible arrangements, and see if you could able to understand the logic behind how to solve these questions, you could be able to solve them easily. So here what will happen, actually the straight part would not be able to contribute any magnetic field at O. So as this element is along the axis of wire, so only curved path, curved wire will contribute to magnetic field. So B is equal to, and we know that for semicircle, for entire loop, what was the formula? It was mu naught I upon 2R for entire loop, but this is for semicircle, so we have to take half of it. Actually for such type of segments we use this formula, mu naught I alpha upon 4 pi r. So we can solve, so here it is angle is pi, so that is why pi will get cancelled and it will be upon 4. So this is what, so directly we can put the value, we can get the answer. So I'm not doing that, I'm just telling you how to do this. So here also this semicircle, and if we grip it, its magnetic field will be along z axis, and if we grip this, magnetic field will be along y axis. So their resultant will lie at the bisector of y and z axis. So this is the first thing. Other thing what you can do is magnetic field by both. B1 is equal to B2. See, I'm not writing in vector form, so I can write them with equality. So that will be mu naught I upon 4R, because it is produced by semicircle, same as this thing. So later on to find B, see, if it is equal to x, then it will be x square plus x square, so that will be x root 2. This will be the resultant. So resultant will be the mu naught I upon 4R root 2. You can put the value, you can get the answer. And in vector form we can leave it as B vector is equal to mu naught I by 4R j cap plus mu naught I upon 4R k cap. That's all. Its resultant is this. Now next here. Now it is a quadrant. Once again, only curved wire will contribute to magnetic field. So I have just asserted it. So I am directly writing B is equal to, now it will become 1 by 4 mu naught I upon 2R. We can put the value, we can get the answer. And in terms of direction, okay, I didn't assign direction to this. So if I grip it, it will go inside. So along negative Z. This is, I grip it like this. Oh, I didn't assign here X, Y, Z. So this is along negative X axis. Here is another question. So, okay, I didn't mention the radius of them. So take it as 1 centimeter and its radius 2 centimeter. So their magnetic field, for first it will come out for outer, and for inner it will go inside. So B will be equal to B in minus, I am taking inside direction as positive, so B in minus B out. And now for circular, for loop, B is mu naught I upon 2R. I am writing it R in minus mu naught I upon 2R out, outer. So you can put the values, so that's not a big deal. And see, if for the sake of simplicity, R in take as R and R out take as 2R, and solve in terms of R and 2R, and later on you can put the value. Take R, R is 1 centimeter, so it is 2 centimeter, that is, put the value R as 1 centimeter, solve it. I'm directly doing this. So similar to this question, it is also same. Actually it is like at the corner of two walls and the floor, there are three quadrants are lying. It looks like a circle, but no, it is a three-dimensional diagram. So for this, magnetic field will go along. Okay, and coordinates are also changed. This is taken as X, this is Y, this is Z. Alright, Z is okay. So how will these current will contribute? So if I write it B1, so its contribution is along negative y-axis. So resultant B vector is equal to B1 minus J cap, and this one will produce B2, let us suppose. So it will point inward toward negative x-axis, that is B2 minus I cap, and this one is like this. So it will point toward negative z-axis, B3 negative k cap. And we can find their magnitude, and all the magnitude will come same. So B1 is equal to B2 is equal to B3 is equal to mu naught I upon 1 by 4 of 2R. And so final result we can find out. And the magnitude of B will be equal to root of B1 square plus B2 square plus B3 square. So if for the sake of simplicity you take it as x, so that will be equal to 3x square, so that will be equal to x root 3. So you can try it of your own. And here there's another question. So here once again contribution to straight wire will be 0, and the angle drawn here is 270, that is 3 pi by 2. So using this formula, B is equal to mu naught I, or what we can do, like here for quadrant it was 1 by 4, now multiply it with 3. So we can say 3 by 4 mu naught I upon 2R. But if we want to go through this expression, then it will be mu naught I, alpha is 3 pi by 2, and then 4 pi R. Then it will be simplified, and finally it will be 3 by 4 times mu naught I upon 2R. So later on you put the numeric values and you will easily get the answer. So that's all in this video. Bye bye.